Okay, so in this recording, we're going to look at alternating series. So our alternating series typically have a negative value that's being raised to the power n, where n is your indexing value for your series. And this will give you positive, negative, positive, negative, positive, negative terms. So we will start with the following theorem. So if we have an alternating series with, here are the important parts. The terms a n here, these have to be greater than 0. Okay. Then, when considering these alternating series, which are basically the same, just if index of n plus 1, index of n, doesn't matter. These series converge when the limit of the terms an, when those go to 0, and when the terms are monotone, non-decreasing. Okay. So why would this be the case? So let's prove this, as I've been doing maybe, and showing you more proofs. We're going to consider maybe this series here. It really doesn't matter which one we consider, they're the same, basically. Maybe we consider the series n equal 1, infinity, that looks like an 8. Infinity, -1 are n plus 1, 8. Okay. So we're going to assume these two things here. So we consider the series and assume this and that. We're going to hope to show that this series converges. An equals 0 and an plus 1 is less than or equal to an. Yeah, so decreasing or non-increasing, I mean, for all n. Okay. Now, the trick that we can do is to look at the partial sums of this thing. And if you think about it, we have positive, negative, positive, negative, positive, negative, positive, negative. If we look at an even partial sum, we can have we can pair up the positives with the negatives. So next, consider S2n, which is going to be equal to, so when n is equal to 1, it's going to be positive. When n is equal to 2, it's negative. So I'm going to group them together like this. N minus 1 minus a C2n. Okay, so one thing to notice here is that each of these terms is greater than 0. It's non-negative, right? Because the sequence of terms A1, A2 is less than A1, A3 is less than or equal to A4. So that's less than or equal to that, so this is greater than or equal to 0. That's less than or equal to that, this is greater than or equal to 0. So maybe I can just say that where an plus 1 less than or equal to an implies this sequence of partial sums, this subsequence, the even partial sums, is monotone increasing. Or non-decreasing. Because we're adding positive numbers to each subsequent term of the partial sums. Okay. Moreover, I'll do this in maybe like green or something. We can also write this as A1 minus A2 minus A3 minus so forth and so on, dot, minus what'll be the last, A2n minus 2 minus A2n minus 1 minus A2n. Okay. You can also write it like that. But now notice again here, we have that, so A3 is less than A2, right? So we're subtracting off a positive number, subtracting off a positive number, subtracting off a positive number, so forth and so on. And that is less than all of these things here. So we see that this A1 is the largest that these sequences could ever be, because each terms they're all non-negative. And this is the first one, the very first one is just A1 minus A2. We see that it's bounded above by A1. So where this implies this is monotone non-decreasing, so it's increasing, and bounded above by A1. And monotone non-decreasing, this is like saying increasing. So monotone and bounded sequences converge by a previous theorem. Thus, the sequence S2n converges by a previous theorem. I'll just say, just for the sake of room, converges to some number, say L, to some limit say L. Just for the sake of room. But that's just a subsequence of the partial sums. We need the full sequence of partial sums to converge in order to determine the convergence by definition of that thing. So we need to consider the subsequence of odd indexed partial sums. Well, for odd index, partial sums. Notice that S of 2n minus 1. So what is S of 2n minus 1 in this picture here? It's really this. This is S of 2n minus 1, right there. So S of 2n plus A sub 2n equals S of 2n minus 1. So for any choice of n, that'll be your n partial sum, which again, this is a sequence. The partial sums are sequences. So then, if we take the limit on both sides, as n goes to infinity, like that, well, we know the limit for the even subsequence of partial sums. We know that's L. That's what we assumed is called an L. But then we also know that the limit, that's a 2n. The limit of a sub n is the same thing as the limit of a sub 2n, and we know that that goes to 0. So it's just plus 0. So since these agree, since both these sequences converge to the same limit, all of the partial sums converge. So since limit of s of 2n equals limit of s of 2n minus 1, limit of Sn equals L. Hence, the sum from n is equal 1 to infinity of minus 1 to the power n plus 1 times a sub n converges as well. It converges to L. There. So that's a proof of the alternating series test. And it's just a little clever breaking up of the sequence of partial sums into even and odd and observing that they collect in a certain way. I kind of like it. Okay, but what would you be concerned with? Well, like I'm sure you just want to see an example, right? How to use it. So all of these questions are about the same problem. Determine the convergence of what series do we have? Alternating harmonic series, looks like. And also I'll put that one up there. A to the power n minus 1. All right, so for the first one, this one is trivial. So the first one here, we choose an to be 1 over n. Clearly, 1 over n plus 1 less than or equal to 1 over n. So a sub n plus 1 is at most a sub n. So it satisfies that piece right there. Also, the limit of 1 over n is equal to 0, so it satisfies that. If it satisfies both, the limit, the alternating series test says that this series here converges. So when you write this down in the exam, be sure to state which test you're using. Right? So you should write down a solution like as clear as possible. So it converges by alternating series. Right. What about this one? This one doesn't quite look like a -1 raised to a power, but we can make it look that way. In fact, we can just say that this is n is equal to 1 to infinity. We can say that that series is actually equal to, if we think about it carefully, -1 to the power n plus 1 times n over 2 to the power n minus 1. Hopefully you can see that those work out. Because basically, the only thing that's changing is the sign of the terms, right? So if we just like look at a -1 and make sure that it matches up. So when n is equal to 0 up here, this will, no, when n is equal to 1, this will be a 0. So this will be positive. When n is equal to 1 here, 1 plus 1 is 2, square root of negative is positive, and it works out. So then, now we just have to look at these terms here. So then notice we have to show both of these things hold. And when you write up your solutions, you should write that very clearly. In fact, this one has like name 1, this one has like name 2. That way you can be like, these terms satisfy part 1, satisfy part 2. Just be as clear as possible. Okay, so let's show part 2 first. So notice that n is, what do I want to say? I need to show that, so what is n plus 1? So n plus 1 over 2n, but replace that by n plus 1, minus 1 goes away. We want to know if this is true. Right? That's what we want to know, which is the same thing as wanting to know if this is true. Oh, wait a minute. So if this is true, then that's true, but we don't know yet. So then how could we show this? Well, this is like saying we divide out. So this is just so then, yeah, so this is true for n, yeah, for n greater than equal to 1, right? But that's always going to be less, and then you just multiply that by 2 over 2, 2 over 2, 2 over 2, get back to this statement here, which implies that. So this, if and only if this is now true. This, if and only if this is not true. We're good. So we've satisfied part 2 over here. Now we just need to show that the limit of a sub n goes to 0. All right, so that's actually not too hard to show because we can just say if f of x equals to x over 2x minus 1, then if we look at the limit as x goes to infinity of x over 2x minus 1, this is indeterminate form. I'm running out of room, but you would use the L'Hopital's rule. Take the derivative on the top, you get 1, on the bottom, you get natural log 2 times 2x minus 1, which equals 0. So it satisfies part 1. So yes, this series does converge by alternating series tests. Okay, so that's just an example of how to use the alternating series test. And all right, let me look at maybe another theorem. Okay, so absolute convergence. So what does this say? It says that if the infinite series of absolute values of A n converges, then the series without absolute value converges. This is the absolute convergence theorem. And I'm out of it today. And then I guess just write down the proof. Notice 0 is less than or equal to A sub n plus absolute value of A sub n, which is at most 2 absolute value of A sub n. Okay, because A sub n is at most absolute value, so we get this bound. So the infinite series equals 1 to infinity. I'm going to stop writing that eventually because it should be taking what's going on. A sub n plus absolute value of A sub n converges since the sum of n is equal to 1 to infinity of 2 absolute value of A sub n, which is just equal to 2 times absolute value of A sub n, that series. Since this converges, and the comparison test, since this converges, and we apply the comparison test. Right, because that's always at most that, right? And since we're assuming that here converges, so this series will converge since that converges. So now we know that this series converges. So then the sum for A sub n this is actually equal to this sum, which we know converges, minus this sum, which we also know converges. Where both series on the right converge. Okay. So we know that that series converges provided that series converges. Okay. So then we should look at like maybe one example. I'll call it a day on this recording. So determine the convergence of function